Neural networks are a revolutionary set of algorithms that have transformed the field of artificial intelligence. They are modeled loosely after the human brain and designed to recognize patterns in data. Just as the human brain processes information through interconnected neurons, neural networks use mathematical models to simulate this process and learn from data. Neural networks excel at machine perception. They can interpret sensory data by labeling and clustering raw input. This makes them incredibly powerful for pattern recognition tasks. Neural networks power many technologies we use daily. They enable image recognition in photos, natural language processing for voice assistants, and predictive modeling for recommendations. Now let's examine the basic structure of a neural network. Neural networks consist of interconnected nodes called neurons, organized in distinct layers. A typical neural network has three main components: an input layer that receives data, one or more hidden layers that process the information, and an output layer that produces results. The neurons in each layer are connected to neurons in the next layer. These connections have weights, numerical values that determine the strength of the connection between neurons. During training, these weights are continuously adjusted to help the network learn patterns and make better predictions. This process of weight adjustment is what allows neural networks to improve their performance over time. In essence, neural networks are powerful pattern recognition systems that use layers of interconnected neurons with adjustable weights to learn from data and make intelligent decisions. At the heart of every neural network lies a fundamental building block, the artificial neuron, also known as a perceptron. This simple yet powerful unit mimics how biological neurons process information. A neuron receives multiple inputs, each representing a piece of information. These inputs could be features from data, such as pixel values in an image, or measurements from sensors. Each input is multiplied by a corresponding weight. These weights determine how important each input is to the neuron's decision. Larger weights mean more influence, while smaller weights mean less influence. The neuron contains a summation function that adds up all the weighted inputs. This is where the magic begins. The neuron combines all the information it receives into a single value. But we're not done yet. The neuron also includes a bias term, an additional constant value that shifts the activation threshold. This bias helps the neuron make better decisions by providing flexibility in when it should activate. The summed value then passes through an activation function. This is crucial because it introduces nonlinearity into the system, allowing neural networks to learn complex patterns and relationships that linear functions cannot capture. Finally, the activation function produces the neuron's output. This output can then serve as input to other neurons in the network, creating the foundation for complex neural network architectures. Let's examine two common activation functions. The sigmoid function squashes any input value between 0 and 1, making it useful for probability outputs. The ReLU function, short for rectified linear unit, outputs 0 for negative inputs and the input value itself for positive inputs. The key insight is that activation functions introduce nonlinearity. Without them, no matter how many neurons we stack together, the entire network would behave like a single linear function, severely limiting its learning capabilities. This single neuron, or perceptron, forms the building block of all neural networks. By connecting many of these neurons together in layers, we can create powerful systems capable of learning complex patterns from data. Neural networks are organized into distinct layers, each serving a specific purpose in processing information. Understanding this architecture is crucial for grasping how these powerful systems work. Neural networks consist of three main types of layers. The input layer receives the initial data, such as pixel values from an image or features from a dataset. The hidden layer, or layers, process this information through mathematical transformations. These layers extract patterns and features from the input data. Finally, the output layer produces the network's predictions or classifications based on the processed information from the hidden layers. In a fully connected network, every neuron in one layer connects to every neuron in the next layer. This creates a dense web of connections that allows information to flow between all neurons. Information flows in one direction through a feed-forward network, from input to output. This unidirectional flow makes these networks particularly effective for classification and regression tasks. While feed-forward networks are fundamental, there are specialized architectures designed for specific types of data and tasks. Recurrent neural networks have connections that loop back on themselves, allowing them to maintain memory of previous inputs. This makes them perfect for sequential data like text, speech, and time series. Convolutional neural networks use specialized layers that apply filters to detect features like edges and patterns. This architecture is particularly powerful for image recognition and computer vision tasks. Each network architecture is designed to excel at specific types of problems. Understanding these different structures helps us choose the right tool for each machine learning task. Neural networks learn through a process called training, where they adjust their internal parameters to make better predictions. This learning process involves two key concepts: the loss function and backpropagation. Training begins with a neural network that has random weights. When we feed data through the network, it produces predictions that are initially quite poor. During the forward pass, input data flows through the network from left to right, producing a prediction at the output. The loss function measures how wrong the network's predictions are compared to the actual correct answers. It's like a score that tells us how badly the network is performing. For example, if our network predicts 0.8, but the actual answer is 1.0, we can calculate the loss using the squared difference. The larger the difference, the higher the loss. Backpropagation is the algorithm that teaches the network how to improve. It works backwards through the network, calculating how much each weight contributed to the error. During backpropagation, error signals flow backwards through the network. Each connection weight is adjusted based on how much it contributed to the final error. The network uses gradient descent to update its weights. Think of it like rolling a ball down a hill to find the lowest point, which represents the minimum error. The gradient tells us which direction to move the weights to reduce the loss. We update weights in the opposite direction of the gradient, gradually moving toward lower loss. The learning rate controls how big steps we take when updating weights. Too large, and we might overshoot the minimum. Too small, and learning becomes very slow. Finding the right learning rate is crucial for effective training. It's one of the most important hyperparameters that determines how quickly and effectively a neural network learns. Through this iterative process of forward pass, loss calculation, backpropagation, and weight updates, neural networks gradually learn to make better predictions and solve complex problems. Activation functions are mathematical operations that determine whether a neuron should be activated or not. They introduce nonlinearity into neural networks, allowing them to learn complex patterns and relationships in data. The sigmoid function is one of the most classic activation functions. Its mathematical formula is f of x equals 1 divided by 1 plus e to the negative x. This function has several important properties. The sigmoid function always outputs values between 0 and 1, making it useful for binary classification problems. However, it has some drawbacks, including the vanishing gradient problem during training. The ReLU function, which stands for rectified linear unit, has become extremely popular in modern neural networks. Its formula is simply f of x equals the maximum of 0 and x. ReLU is incredibly simple. It outputs 0 for negative inputs and passes positive inputs unchanged. This simplicity makes it computationally efficient and helps solve the vanishing gradient problem that affects sigmoid functions. There are several other important activation functions worth knowing. The Tanch function outputs values between -1 and +1, making it zero-centered. Leaky ReLU addresses the dying ReLU problem by allowing small negative values to pass through. Choosing the right activation function is crucial for neural network performance. ReLU is often the default choice for hidden layers due to its computational efficiency. Sigmoid is useful for binary classification outputs, while TON works well when you need zero-centered outputs. The choice depends on your specific problem, network architecture, and training requirements. Deep learning represents a revolutionary advancement in neural networks, achieved by stacking multiple hidden layers to create what we call deep neural networks. While traditional shallow networks have only one or two hidden layers, deep networks contain many layers, often dozens or even hundreds, allowing them to learn increasingly complex patterns. The key advantage of deep learning lies in hierarchical feature learning. Each layer learns to detect increasingly complex features, building upon the simpler patterns learned by previous layers. This hierarchical learning capability has enabled breakthrough applications across multiple domains. Deep learning powers modern image recognition systems, natural language processing, and speech recognition technologies. However, training deep neural networks presents significant challenges. The vanishing gradient problem occurs when gradients become exponentially smaller as they propagate backward through many layers, making it difficult for early layers to learn effectively. Fortunately, researchers have developed several techniques to address these challenges. Batch normalization helps stabilize training by normalizing inputs to each layer. Skip connections, used in architectures like ResNet, allow gradients to flow directly to earlier layers, bypassing the vanishing gradient problem. These innovations have made it possible to train networks with hundreds of layers, unlocking the full potential of deep learning and enabling the artificial intelligence breakthroughs we see today. Neural networks have revolutionized countless industries through their practical applications. Today, we'll explore 5 major areas where these powerful systems are making a real difference in our daily lives. Image recognition is one of the most visible applications of neural networks. These systems can identify and classify objects, people, and scenes in photographs with remarkable accuracy. Natural language processing enables computers to understand and generate human language. This powers machine translation services that can instantly translate between dozens of languages, and sentiment analysis that determines whether text expresses positive or negative emotions. Speech recognition systems convert spoken words into text in real time. These neural networks can understand different accents, handle background noise, and even work with multiple speakers simultaneously. Recommendation systems analyze your past behavior and preferences to suggest products, movies, or content you might enjoy. These systems power the suggestions you see on streaming platforms, online stores, and social media feeds. Self-driving cars represent one of the most complex applications of neural networks. These systems must process camera feeds, radar data, and sensor information in real time to make split-second decisions about steering, braking, and navigation while ensuring passenger safety. These applications demonstrate the versatility and power of neural networks. From recognizing faces in photos to powering autonomous vehicles, neural networks are transforming how we interact with technology and opening up possibilities we never imagined before. Neural networks are powerful tools, but they come with significant limitations. Understanding these challenges helps us appreciate current research directions and future possibilities in artificial intelligence. First, let's examine 3 major limitations that researchers and practitioners face when working with neural networks today. Neural networks are extremely data hungry. They typically require thousands or millions of training examples to perform well. This creates barriers for applications where data is scarce or expensive to collect. Neural networks are vulnerable to adversarial attacks. Small, carefully crafted changes to input data can fool networks into making completely wrong predictions, even when the changes are invisible to humans. Perhaps most concerning is the black box nature of neural networks. It's often impossible to understand why a network made a particular decision, making them unsuitable for critical applications where explanations are required. Despite these challenges, researchers are actively working on solutions. The future of neural networks looks promising, with several exciting developments on the horizon. Explainable AI aims to make neural networks more transparent. Researchers are developing methods to understand and visualize what networks learn, making their decisions interpretable and trustworthy. Neuromorphic computing involves building computer hardware that mimics the structure and function of biological brains. This approach promises more efficient and brain-like artificial intelligence systems. Attention mechanisms allow neural networks to focus on the most relevant parts of their input, similar to how humans pay attention to important details while ignoring distractions. Generative models can create entirely new data samples, from realistic images and text to music and code. These models are revolutionizing creative applications and data augmentation techniques. The field of neural networks is rapidly evolving, with new breakthroughs happening regularly. Whether you're interested in solving current limitations or exploring future possibilities, there has never been a more exciting time to dive into this field. Start by taking online courses, experimenting with frameworks like TensorFlow or PyTorch, following research publications, and joining AI communities. The neural network revolution is just beginning, and your contributions could help solve some of humanity's greatest challenges.